Let's look at the solutions of Quant Crusades for 23rd April now. If k is the product of all natural numbers between 2 and 200 that have odd number of factors, what is the highest power of 16 that will divide k? If we are looking for highest power of 16, we are looking for highest power of 2 raised to the power 4. And we are looking for numbers that have odd number of factors. So we are basically looking for perfect squares. And we are looking for 2 raised power 4. So we are looking at even squares that lie in the range 2 and 200. So the numbers that are useful to us are 2 square, 4 square, 6 square, 8 square, and how much? 10 square, 12 square, and 14 square. Let us see how many powers of 2 are present. 2 raised power 2 this is, 2 raised power 4 this is 2 square into 3 square. We are only concerned with power of 2, so 2 square. This is 2 raised power 6. This is 2 raised power 2. This is 2 raised power 4, 16 into 9. And this is 2 raised power 2 again. So altogether, I will get 2 raised power 2, 4, 2, 8, 8, 6, 14, 14 plus 8, 2 raised power 22 into something, 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 something. And I have to divide it by 2 raised power 4. So 2 raised power 4 raised to the power 5 into 2 raised power 2, something, 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 divided by 2 raised power 4. So highest power that can be included is option C, 5. Next, find the sum of all natural numbers from 1 to 100 that are neither a multiple of 3 nor a multiple of 4. Okay, so first, how many numbers, sum of all numbers from 1 to 100 would be given by 100 into 101 divided by 2. This is sum of all numbers minus numbers that are multiple of 3. So 3 into, there are going to be 33 such numbers. So sum of 33 first natural numbers is given by this minus sum of all numbers that are multiples of 4. So 4 into 25 into 26 divided by 2. The problem is right now I have removed multiple of 12 from here also and multiple of 12 from here also, but it should be removed only one time. So I have to add that back. So 12 into how many multiples of 12? 8. So 8 into 9 by 2. Okay, let me break this down. I get 5050 minus, this will be 17 into 3 or 17 into 99. So 1683 minus, cancel 13, 4 into 25 is 100 minus 1300, cancel 4. So 12 into 4 is 48, 48 into 9 is 432 plus 432. So I will get how much? 5482 minus 2983. Okay. So 5400 minus 2900 leads me to 2500, one less than that. Answer should be 2499 or option B here. Next question. How many ordered pairs of PQ are there where both P and Q are non-negative integers such that P minus 1 by Q is equal to P by Q plus 5? Let's write this down. P minus 1 by Q is equal to P by Q plus 5. So PQ minus 1 is equal to P plus 5Q. Let me get all the P terms on one side, all the Q terms on the other, or Q and the constant term. So I get P in common. Q minus 1 is equal to 5Q plus 1. Or P is equal to 5Q plus 1. Or by Q minus 1. Or P is equal to 5Q minus 5 plus 6 by Q minus 1. Or P is equal to 5 plus 6 by Q minus 1. 6 by Q minus 1. Now Q minus 1 has to be a factor of 6. Q minus 1 has to be a factor of 6. And how many factors of 6 are there? The factors are 1, 2, 3, and 6. So q minus 1 is equal to 1 where q is equal to 2, or q minus 1 is equal to 2 or q is equal to 3. So if q minus 1, these are values of q minus 1, q can take values of 2, 3, 4, or 7. And correspondingly, every time you'll get a new value for p. So how many possibilities? 4. Next, what is the largest power of 3 that will divide 7 factorial plus 8 factorial plus 9 factorial plus 10 factorial? Some of us may be smart enough to know the precise values. For those of us who aren't, please watch this. 7 factorial, I can take out common. I'll be left with 1 plus 8 plus 8 into 9 plus 8 into 9 into 10. So this translates to 9. These together translate to 81. 8 into 9 into 10 is 720. 720 plus 81. So we have 7 factorial into 801, which I can rewrite as 7 factorial into 89 into 9. Now within 7 factorial, how many 3's will I have? I will have 3 square into something something into 89 into 3 square. What is the largest power of 3 that will divide this expression? It has to be 3 raised to the power 4. So option D. Next, in the value of the number 18 factorial, all trailing zeros are erased. Find the unit digit of the left number. Okay, 18 factorial, I have to prime factorize it. Hopefully we know this. If we are looking at a power of 2, let's say we are looking at 16. In 16 factorial, we have 2 raised to the power 15. Or in 8 factorial, we have 2 raised to the power 7 and other prime numbers. So when we are looking at 18 factorial, can I say straight away 18 factorial? Prime factorization is easy. This is a small number. So we'll have 2 raised to the power 16. In total, we will have 2 raised power 16 because up until 16 factorial, we have 2 raised power 15. And then from 18, we'll get one more 2. For 3's, every 9, every n square. The other idea is n square factorial divided by n. If I do n raised to the power k, the value of k is equal to n plus 1. So in every 9, you get 4 3's. So in 18 factorial, you will get 3 raised to the power 8. Then we've got 5, which will be cube. Everything after this is fairly simple to manage. 7 square, 11 raised to the power 1, 13 raised to the power 1, 17 raised to the power 1. Now, if all trailing zeros are erased, all 2's and 5's have to go. So 5's gone and 2's will reduce to 2 raised power 13. And now I have to find out the unit digit of this leftover expression. This gives me unit digit as 2. This gives me unit digit as 1. This gives me unit digit as 9. This gives me unit digit as 1, 3, and 7. 3 and 7 give me unit digit as 1. 9 and 2 give me a unit digit as 8. The answer to the question has to be option A. Next, which of the following divides 13 cube plus 15 cube plus 20 cube plus 18 cube? Now, this wonderful question expects you to notice this. Can you see 3 is a part of every option, all the 4 options? So the number is definitely divisible by 7. This much we know. Next thing we see is we have a multiple of 7 here. We have a multiple of 7 here. This is 7 into 3. This is 7 into 2. Is this entire expression an even number? Odd plus odd, even plus even plus even? Yes. So if it is divisible by 3, it has to be divisible by 4. If it is divisible by 3, it has to be divisible by 4, which at this time eliminates option A and option 3. It will either be B or be D. Let's see if this expression is divisible by 3. So I know this number is divisible by 3. This number is divisible by 3. In 13 cube, I'm left with 1 cube. In 20 cube, I'm left with minus 1 cube. So if I add these up, overall remainder with 3 is of course going to be 0. So the number is indeed divisible by 21 also. Number is divisible by 7, by 14, by 21. Answer has to necessarily be option D. You did not need to check it with 11. Even if you did, it would not be a problem. With 11, here you get a remainder of, let's say, plus 2 cube. Here you get of minus 2 cube. Here with 11, you get a remainder of plus 4 cube. Here you get a remainder of -4 cube. So altogether you will get 0 remainder with 11. You can reach your answer if you were checking with 11 also, but that was not important for this question. Next, find the remainder when 71 raised to the power 11 factorial raised to the power 71 is divided by 11. Now we know that a raised to the power b minus 1 by b gives me remainder 1 when a and b are coprime and b is prime. Is 71 and 11 coprime? Yes. Is this power here a multiple of 10? Is this power here a multiple of 10? Very much so. 11 factorial is a multiple of 10. So directly you can jump to the conclusion. Remainder here is 1. Next, for all the possible integers n satisfying this expression, how many integer values of 2 plus 2 raised to the power n minus 2 are possible? Far too many people fall into the trap of working with this expression first. That comes much later. Look at this right now. If you want this to be an integer, this is an integer. You want this to be an integer. If you want this to be an integer, the worst case scenario would be power of 2 here turns out to be 0. So n has to be greater than equal to 0. N has to be greater than equal to 2 on account of the second expression. Now let's look at the first expression. We've got 3.2 is less than equal to 3 plus something is less than equal to 250. Only looking at the subsequent expression, can you see 3 plus 3 raised to the power 5 is less than equal to 250, which means n plus 3 has to be less than equal to 5 or n has to be less than equal to 2. According to the second part of the first expression, n has to be less than equal to 2. According to second expression, n has to be greater than equal to 2. So how many integer values are possible? Only when n is equal to 2 do you get an integer value in the second case. So answer is option A. Next one. The minimum number of equal squares that can be cut from a rectangular cardboard is 90. If both the length and breadth of the rectangle is a positive integer between 25 and 32, find the area of the rectangle. Okay, let's see. If we are saying number of squares that can be cut is 90, effectively what we are saying is let the size of each square be n. This is n and this is also n. This entire thing will be kn and this entire thing will be mn. What the question is telling me is k into m is equal to 90. K into m is equal to 90. In fact, for the dimensions, can I say L is equal to mn and k is equal to breadth is equal to kn, and this n here serves nothing more than the HCF of two numbers. HCF of two numbers, whereas m and k are coprime. So we now need two coprime numbers to multiply to give me 90. Let's look at all the possibilities. 1 into 90, 2 into 45, 3 into 30 wouldn't work. That is not coprime. 5 into 18. And next would be 6, no. 9 into 10. These are all the coprime pairs that you can make out of 90. Now see, m and k are coprime. If we want HCF of two numbers is n. If these were the two sides, can you see 1 and 90? Because the sides have to stay within this, range. Even if I took HCF as one of the two sides will exceed 32. So this is not possible. Similarly, in this one, this will exceed 32, not possible. Here it will not exceed. So let's check. When HCF is 1, I get sides as 5 and 18. That wouldn't work. We need sides between 25 and 32. When HCF is 2, sides would be 10 and 36. This is also unacceptable because this is lower than 25. This is higher than 32. So this would also not work. So this pairing is also not serving the purpose. Let us check for the last grouping. Let's say if HCF was 1, we would have 9 into 10. This doesn't work because we want the length of our sides to be 25 and 32. We're not getting that. Let's go to, so we'll have 18 into 20. Still doesn't work. We need sides to length to be between 25 and 32. Let's take HCF3. We'll get 27 into 30. Yes, everything works out well. Will we have any more cases? 4 would be 36 into 40. We have crossed the threshold of 32. So no, this doesn't work. The only acceptable case is if the length and breadth were 27 and 30, and therefore the area of the rectangle turns out to be option C, 810. While the explanation takes a lot of time, hopefully, if you're comfortable with number fitting, you would be able to arrive at your answer much, much faster here. Last question. What is the second non-zero digit from the right end in the product of the first 20 multiples of 5? Okay, first 20 multiples of 5. Product of first 20 multiples of 5 is as good as 5 raised to the power 20 into 20 factorial. Hopefully, we remember our skill from the first question, wherein we can go 20 into 16 and 4. So 15 and 3. So 2 raised to the power 18 into 3 raised to the power 8 into 5 raised to the power 4 into 7 raised to the power 2 into 11 raised to the power 1 into 13 raised to the power 1 into 17 raised to the power 1 into 19 raised to the power 1. We are now looking for, we are removing second non-zero digit. So first we have to remove all the zeros from the expression. So 18 2s and 18 5s will go away. I'll be left with this number now. I'll be left with this number. And now I now need the last 2 digits. If I want the second non-zero digit from the right, I need the last 2 digits. Last 2 digit is nothing but remainder with 100. So I need remainder with 25. I see that the product is divisible by 5 raised power 6. So the number has to be a multiple of 25. This much I know. I also need remainder with 4. If I have remainder with 25 and I have remainder with 4, my work will be done. If I need remainder with 4, here I get minus 1 raised to the power 8, so 1. Here I have 1 raised to the power 6, so 1. Here I have minus 1 raised to the power 2, so 1. I have minus 1 raised to the power 1, so minus 1. 13 raised power 1, so 1. 17 raised power 1, so 1. 19 raised power 1, so minus 1. Altogether, if I multiply all of this, I'll get 1 only. So remainder with 4 is 1. Remainder with 25 is 0. If I combine these, I will get 100n plus 25 itself. So the second last digit of the product, non-zero digit of the product, will be 2. And that is all for this test. Hopefully you learned something and you're more comfortable with number system throughout the week. Okay, bye people.